if any of you didn't do it, just could you write me on some piece of paper, and I will send you a reference for this lecture. Okay. This is only next Friday. All further lectures will be in usual form.
А можете надеть микрофон? Вроде запись пошла.
Okay, let's start. Today we do most homological algebra, so we just need to prove some standard facts on projective resolutions to be sure that the homology groups are well defined. The homology groups we defined last time are well defined. So. Of course, maybe some of these topics are well known to some of you, so but still, to be consistent, I need to give this introduction. Okay, so first of all, the main definition that we are always working on over some ring. I always assume that there in R is associative ring with unit. But the main example for me is the group ring of a group. This is not required at the moment, but this is the main and the only example, almost the only. Actually, this can be also a group ring over some commutative ring. Except instead of that, we can take, for instance, Q or some other commutative ring. So this is almost the only example. Sometimes I will just restrict ourselves to this example. As I have said last time, this example is more convenient than the general situation, since we are able to pass from right modules to left ones and vice versa whenever we want. So since this ring has a natural anti-automorphism. Okay, but for me it is important that this ring is not required to be commutative, since in most applications it will not be commutative. So, well, I usually prefer to work with left modules. However, situation with the right modules is more or less the same. So suppose that P is an R module. Then P is called projective. If and only if, this is a definition, it is called projective, if the following functor is exact. So we consider G equivariant homomorphisms from, I always try to to think over the G. We take homomorphism, we take homomorphism of R modules from P to some other left R module, and this is a function of this second argument. And the requirement is that it is exact. This means that it takes exact sequences to exact sequences. So if we have exact sequence of, I prefer to write it here, if we have an exact sequence of R modules, then of course, here I and J are just homomorphisms of R modules, then of course we have induced exact sequence of induced sequence of sorry. From P to B, and finally we have from P to C. So of course we always have, for any module P and any such sequence, we have it produces a sequence of such modules. Note that hom is covariant function in this argument. The requirement is that this sequence, for any sequence, initial sequence, this sequence will be exact. For any exact initial sequence, this sequence is always exact. Of course, exact, what does it mean exact? First of all, this means that the composition is trivial. And second, this means that the kernel of G star is exactly the image of I star. The first part is trivial. The first part holds for any module P. So if we have any module P and any such exact sequence, then in this sequence the composition will get trivial. So we only need to check. So we always have, what does it mean that the composition is trivial? This means that we have inclusion, the image is contained in the kernel, and we only need to prove the inverse inclusion. So we need to prove that if some homomorphism is in the kernel of G star, then it lies in the image of I star. What does it mean? If we have a homomorphism from P to B, then then the requirement that this homomorphism is in the kernel of G star is exactly that this composite homomorphism is 0. And our P is projective if and only if any such homomorphism phi lies in the image of a star. So if and only if any such homomorphism admits such lift to a homomorphism to A. So this is exactly to say that this module, this function is exactly equivalent to saying the following: for any exact sequence of R modules and any homomorphism from P to B, which is 0 composed with J, there exists a homomorphism from P to A, which together with I gets phi. So for any phi such that phi and then J is 0, there exists psi such that psi is psi composed with I is phi. So this is a definition, and first trivial fact that any free module is projective. Well, a free module is just is just a direct sum of several copies, of several maybe of infinitely many copies of R. So a free module is by definition a module which is not necessarily of which is direct sum of several over some index set of copies of the R itself, considered as left module of itself. And well, of course, any free module is projective. This lemma is completely trivial. If we have free module here, then we have basis elements. Let us write this form that it is R trivial R module as a move to R with generator EI. Then, if P has this form, then we just can choose for C of E alpha, C of E alpha are chosen so that they go to phi of E alpha. Since phi of E alpha lies in the kernel of G, then it lies in the image of I, so we can choose C of E alpha so that it goes here to phi of C alpha, and then just extend this psi to the whole direct sum. This problem of lifting is always solvable, which means that the module is indeed projective.
Should we consider the shortage sequence such as definition and not this exact sequence?
It is enough to consider shortage sequences, but one can consider.
I mean, isn't that true for any module? I mean, this diagram. I mean, it's exact. I mean, yeah. After applying the one factor to this diagram, it is accurate.
Yes, yes.
So I mean, we don't need ideas. I mean, this is true for any.
No. It is true for any module that if what is true for any module? If you have short exact sequence, then this sequence will be exact in the middle term. But it is not true that if you have just this is not short. This is two short exact sequences. We don't require that this is surjective and this is injective. If we just ask for any such sequence, then it's a general case. Well, the matter is that any non-exact sequence consists of such short exact sequences, of such very short exact sequences. Well, this is just a piece of any. So if we require that this is if we require exactly what I have required in this situation, then it automatically takes any exact sequence to any exact sequence. So, yes, but this is an important remark that it is enough to require that equivalently one can require that any short exact sequence is taken to a short exact sequence. But okay. Well. This is first thing. Well, also, the second trivial lemma is that an R module is projective if and only if it is a direct sum of a free module. So let us prove this. Well, let us first prove it from right to left. Suppose that it's better to start from left to right. Well, suppose that we have a projective module. P is projective. Note that it is rather easy to make any module a quotient of a free module for any module, even not projective. Just this is a general remark. Any module is a quotient of a free module. Suppose that you have any module M, then just take all elements of M and take them as a set of the set of all elements of M. We can just forget about the structure of the model and consider this just as a set, and take the free module with such basis. So we take all elements of M, but now forget about all operations. Just take in mind only this set, and just take them for new basis elements. Just these letters are basis elements of left R module, of left free R module. Then of course you have morphism, natural cohomorphism here, which takes any n, considered here as an element of the basis, to this m itself. And then you can extend it by linearity to the whole free R module. And of course, this is surjective, since any m is in the image. So we always can include any module to such sequence where f is free. Sorry. One moment. I forget to say it here, and maybe now it's also a moment for this. When I'm saying a direct sum, I always mean that only finite linear combinations are allowed. So we cannot take infinite, even if the set A is infinite, we are not allowed to take infinite combinations of basis elements. All sums are only finite. Okay, now suppose that our module is projective. As before, we consider such sequence for this P, and we consider the identity morphism from P to itself. Of course, we see this situation. Of course, this composition is trivial, since the module here is trivial, so there exists an extension here. So let this be J, and then there exists F such that the composition F and then J is the identity homomorphism of P. But what does it mean? This means that F is, first of all, this means that F is an injection, it is objective, and that F is the direct sum of the image and the kernel of J. Okay, so this one is isomorphic to P, since it's injected. So we obtain that this P is a direct sum of free. Okay, this is one way. And another way, vice versa. Suppose that there is a free module, and the module P, which is interesting to us, is a direct summand of it. So we have such decomposition, where Q is any module. We need to check that P is projective. So we need to check this property. Suppose that we have such diagram, and at the moment we do not know whether there is such lift. But having such diagram, we always can take here, write here P plus Q, and extend here by 0. So we just take the homomorphism phi plus 0 homomorphism of Q. And now we know that this one is free, hence projective by lemma 1. So for the module F, we have this property and we have this homomorphism. And then its extension to P is the required homomorphism. So this is also very simple. Okay. Yes, one thing which I need to say is that at this point a natural question is whether any projective module is free. Okay, of course any free module is projective, but whether there exist projective modules which are not free. For some reasons, it is true that any projective module is free. For instance, for if R equals Z, then it is a good easy exercise that any projective module. Oh, well, this exercise is so easy that I even don't want to just to. It's not so. Any projective module is free. Well, the exercise is completely trivial for finitely generated models, since that module is just an abelian group. We know the classification of finitely generated abelian groups. So, of course, any finitely generated abelian group is a free abelian group plus some torsion. Of course, torsion, if a module contains torsion, it cannot be projective, since it cannot be a direct summand of a free abelian group. So, in a finitely generated case, this is completely trivial. In not finitely generated case, it requires, well, it is still very simple, but I don't want to discuss now, it's a good exercise. But I want to mention that here there are very complicated and hard problems. And for instance, if R is just the polynomial ring, then this was a famous Serre's problem, Serre's conjecture. That any projective module is free, and it was proved by Gayfullin and Suslin independently, and this is a really hard theorem, so it is of course not easy. Well, but there are also plenty of examples of where when a projective module is not free. There are many sources of such examples, but in our context, the most important example is as follows. I would like to give this example. Of course, there are some examples over matrix rings, over commutative rings, but for us, of course, the most important case is group ring. So I would like to give an example of this kind. And actually, the claim is the following. So, proposition. Okay, there exist examples of such kind over ZG, but I don't want to give them. They are somewhat harder. But the most trivial example is KG, where K is a field of characteristic 0. So I consider this case. Proposition. Suppose that G is suppose that G is a finite group. Then any G module is projective. Any R module, any module over this group ring. I will prove this in a moment, but just now let us note that, of course, not any module is free. For instance, we always have this trivial example. We always can consider the field K as a KG module, just with trivial action of G. Any element of G acts trivially with respect to trivial action of G. So, well, this one is projective in particular by this theorem, but it is not free. Of course, I assume that the group is not trivial. Why it is not free? Because, of course, if the order of the group G is n, then any free KG module, we can consider its dimension just as a vector space of G. And of course, the dimension of any free module is divisible by n, since it's a direct sum of KG. But here the dimension is 1, so of course it is not free. And we have plenty of other modules that are not free, but all modules are projective. Why? The proof is rather simple, but it uses, well, an important idea, which we all have already met. This idea. So suppose that we have this such exact sequence, and we have here a homomorphism phi. Well, P is just an arbitrary module. I want to prove that it is projective. We have a homomorphism phi, which goes to 0 here. Well, now forget for a moment about the structure of our module. All our modules are, of course, vector spaces over K. So just forget about the structure of our module and just keep in mind the structure of vector spaces over the field K. Then, of course, when you have a homomorphism of vector spaces, which, well, over a field, all modules are free. And hence all modular projected, and this is very trivial, that over a field we always can find such Lifton. So we always can find here this Lifton F, which is not a morphism of R modules, but it is a homomorphism of, so F is just a homomorphism of K vector spaces. Now I would like to construct a homomorphism of R modules with the same group, and it is made by easy averaging over the group G. So I just for this GF I can activate by the elements of group G, and I can take an average. So the required homomorphism psi of X, well, X we take from P, is by definition it's just the following. We take the average over G, and here we have the following sum. We take F of Gx, and here apply G minus 1. So this is the action of G on P, and here we, since all these are modules, we can write down that formula. Well, and now first of all, it is a morphism of R modules.
Psi is from where to where?
Psi is so, but F doesn't know anything about the structure of module over history R. It is not equivariant. But this one is G equivariant. So it is a homomorphism of R modules.
How we build F by
F, the matter is that if we deal just with vector spaces, if we have a vector spaces over any field, then this Lifton property is trivial. If you have a morphism of vector spaces,
is that morphism this P?
this F. Okay. Once more, from the very beginning,
Yeah.
we would like to prove that the module P, we take any module P, and we would like to prove this property without Q. This is Lifton property for this P. We take any exact sequences of R modules. R is this group L. We take any homomorphism to B such that the composition is zero. Now we all these arrows are morphisms of R modules. But now we forget about the structure of R modules and just look on this diagram as a diagram of K vector spaces. If we look at this diagram as a diagram of K vector spaces, over a field, all modules are free.
Yes.
So we have this extension.
Yes.
We have this extension, but this F is not. Now we remember about the structure of R modules, and of course this F can be not a homomorphism of R modules. So it is always K linear, but it cannot be G equivariant. So we would like to construct a G equivariant morphism, and it is obtained by such averaging procedure. It is an easy check that this is indeed G equivariant if we act by an element of G. Yes. Then we just have the situation like that, just by definition. Okay, but now we can do like that. We can insert here h minus 1. Well, this is just unit, and then this one is the inverse of that, and redenote it by g. So we have we get 1 over module g. We can take this h out of the sum sign, so we have h g inverse f of g. So we get h times psi of x. So we have this easy calculation which shows us that this psi is equivalent. And of course, this together with I, we have this phi. We have it for the initial f. Again, this is a simple check that this mu homomorphism psi still satisfies. Well, the matter is that any of these homomorphisms satisfies this property. So since these two are G equivalent, if we act by G, then if one is satisfied, then all other also satisfy this property, that the composition is phi. And hence, after averaging, we still have this property. Well, why we need here characteristic equals to 0? Since we would like to be able to divide by the order of G. Actually, the same is true if the characteristic is co-prime with the order of G. Okay, so we see that any module is projected. So at least I just wanted to show you that not all projected modules are free, and we have plenty of such examples. But actually, this observation is sometimes useful by itself. Okay, and also we have these two trivial lemmas, but also I want we have one more rather easy lemma. Well, I will be interested in such two functors. We have function of tensor products. With some fixed module, and we have the functor of homomorphism from any given from some module to the given module n. These two functions will be important for us. Of course, if I work over any associative here I must assume that this module is right. But if I work about group ring, I can always consider all arguments to the left modules, as we discussed on the previous lecture. And then the claim is that, this is a rather well-known fact, but I would like to remind you just that this one is a right exact module functor, and this one is a left exact functor. I will remind what does it mean, and I think that I will left this as an exercise for those who don't know this. This is a rather easy exercise. So this means the following. Well, now, at this moment, I would like to consider short exact sequence. So I want to be more restricted than here. Here we just have two. Here we do assume that J is surjective and I is injective. Now I want to assume that they are. And once we have this situation, first of all, for the first functor, we can take the induced sequence of this one is sequence of R modules. This one is only sequence of abelian groups. I recall that if we have a ring which is not assumed to be commutative, then we have no module structure on the tensor product. So this is just an abelian group. Well, but we have this sequence. Well, and right exact means that, well, of course, means that this is not true, but this sequence will be exact. So we still have, can say that this G star is surjective. This is exactly in this term. We still know that the image of I star coincides with the image of G star, but we cannot guarantee that I star is injective. So this is called right exactness. Yes. Well, so this is right exact, and left exactness means that well, over for this functor is contravariate, and here we have Cohom from and here we have this sequence will be exact. So we always knew that G star is injective, I star has the kernel of I star coincides with the image of G star, but we cannot guarantee that this E star is surjective. So, well, this is all. These two. This is always true. And this is a good exercise. Well, but it is important to have a condition when let us speak about the first of these functors, under which the function is completely exact. The functor is exact if the whole short exact sequence becomes short exact sequence. And a useful claim is that, well, first of all, this situation is called flat module. So, by definition, an R module N is flat if this functor is exact. So short exact sequence will go to a short exact sequence, and then any exact sequence will go. Any exact sequence can be decomposed into short exact sequence. So then any exact sequence will go to an exact sequence. And important for us claim is that projective modules are flat. So working with projective modules, we can use the exactness of gender problem. Okay, why this is true? Well, the proof is in two steps. First, trivial. Trivial observation is that free modules are flat. Okay, if this module n is free, then a tensor product, well, it's easy to see that any module tensor product with R is just A itself. It's a trivial observation. So if we take tensor product with a free module, which is such sum of modules isomorphic to R, then we have a direct sum of modules R. Okay, just copies of modules R indexed by alpha. So, of course, if we take such sequence and replace each module, just take direct sum of several copies of it here, of the same number of copies here, and consider the corresponding, of course, the sequence will be still there. So, for free modules, it is trivial. And second, we would like to prove this for any projective modules using this lemma 2. So if P is projective, then we know that we can find a free module such that it is a direct sum of P plus R. Well, then I want to show it here. Okay, so we know that since F is projective, we know that this sequence, we only need to prove exactness in this term, since in all other terms it is always exact by our exercise. So we need only to check that this one, we know, not we need to check, we know that this one is injective since a free module is flat. But this one is equal to the direct sum and here we have the same decomposition for B. And of course, the first summand maps to the first summand here, and the second summand maps to the second summand. So if we know that the whole homomorphism is injective, then the first homomorphism is also injective. So actually it is trivial that if a module is flat, then any direct sum is flat. So in particular, all projective modules are flat. the inverse station is not true, even over, so just remark that even if we take the simplest possible ring, just Z, then we have such module, a module Q, which is flat. Well, it is trivial, but if we have a short exact sequence of abelian groups, then transit by Q, it will be a short exact sequence of Q spaces. So it is flat, but not projective. Of course, it is not, since it cannot be a direct sum of a free abelian group. Okay. Well, and starting from this point, let us let us always assume that the ring is the group ring, or the group ring with coefficients in F. This is also possible. Well, actually, a definition which is also can be given over any ring, that if we have a chain complex suppose that we have a chain complex, it can be infinite at that side, but not related. PP0 is last one. So suppose that this is a chain complex of G modules. I recall that G modules are exactly modules over this ZG. Starting from here, I always assume all modules left. So suppose we have a chain complex of G modules, and this chain complex is called a resolution for a module M. If the homology of this chain complex, well, the homology is, as usual, the kernel of one of their, well, let this be 3 and so on. So nth homology of a chain complex, as usual, is the kernel of nth homomorphism by the image of n minus n plus first. By the image of the previous one. So it is called a resolution for module M, if and only if the homology of this chain complex is M in dimension 0 and is trivial otherwise. In other words, it is a resolution for M if it is better to say that a resolution is a chain complex together with a homomorphism from B0 to M. So it is a resolution if if the following complex sequence is exact. Of course, all arrows must be homomorphic of G modules. Well, of course, just it is not interesting to consider any resolution. Well, since we can always write down this very simple resolution for any module M, and this is not interesting. It is interesting to consider resolution consisting of relatively big modules. So the most useful is the notion of projective resolution. So if a resolution is projective, or if all modules here are projective, it is free if all modules are free, and so on. So for us, it will be an important notion will be projective resolution. Resolution considered consistent of projective modules. Of course, first of all, about existence. Of course, any module has a free resolution. Why? As before, we have here a module. We can construct a free module which maps with subjectively. Just by taking all elements of M as generators and map. Okay, this map has some kernel. We would like to kill this kernel. So we can consider, we can construct a free module which maps subjectively onto this kernel. Again, by taking all the elements of kernel as independent variables and so on. And of course, we are always able to get a free resolution. Of course, this free resolution which I have just described is impossible to work with. But an important thing is that in good cases, the resolutions can be found, can be taken to be rather natural. And I would like to recall that last time we constructed, starting from some geometric construction of a configuration space, we have constructed a free resolution for Z over Zg. The most important case is free and hence projective resolution for Z over Zg. At the moment, I just want to recall the construction. Why it is a resolution I explained last time. So the idea is that for Pn, for this module Pn, we take free Zg module with bases, with generators, consisting of such elements, of such symbols, G1, Gn, where Gi are elements of G not equal to 1. And these maps I usually denote by D, and this differential, I just would like to recall that the differential of this element is written as follows. Minus G1, G2, G3, and Gn, plus and etc. The signs alternate, and the last one, the last two are as follows: G1, etc., and the last two are multiplied, and in opposite side with where the last one is just removed. Okay. And I remind that here we assume all symbols where at least one group element is 1 to be trivial. Well, just a good, this one is called a normalized bar resolution. And last time we have proved that it is indeed a resolution. Well, of course, it's free resolution. That it is indeed has the required homology.
You don't quantify those terms by engineering?
No. No, exactly as so the corresponding sequence will be exact, except for this term, where we have homology Z. To guarantee this, we will just do this for. A good exercise is that sometimes it is more convenient not to normalize the resolution. And this means the following. That alternatively, one can take a bigger ZG module, namely one can take for the basis all such elements where units are also allowed. So all with GI in G. And write down the same, just the same formula. A good exercise that it is also a resolution for also the G resolution for G. For Z. Well, actually, you need not again move to topology to do something. It is just a rather easy exercise to understand that these module and these complex and this complex have the same homology. So this is not hard. And, so this is not normalized. This is usual bar resolution. Sometimes it is more convenient to work with this one, sometimes to work with that one, but both of us. Okay, and well, so now we are going to deal with homology. So the next important object is functors tor and x. These are two functors which measure. We know, we have already discussed that, well, these two functors are sometimes not exact. So they are. The first one is right exact, the second is left exact, but they're not exact in general. So these derived functors, they are called derived functors, measure how these functors, these two functors are not exact. So the idea is as follows. Again, this also can be done over any ring, but you need to say which modules are right and which are. Okay, the idea is as follows, that we take a module M and write down a resolution for M. A projective resolution for M. So this is a projective resolution for M. I mean that this is exact and M is not supposed to be projective, so the resolution itself is this part. Okay? So suppose you have a projective resolution for M, and then you can, so this sequence is exact. But now you can tensor this sequence with another given module N. So you can consider this sequence. And so on. This is a sequence of a given groups, and it is not necessarily exact. And its homology is exactly the functor Tor. So this is called Tor. It has this functor has just index which goes from 0 to which is non-negative integer, and it is usually written Tor G since it is over group G, or if it is over any associative ring, just Tor over this ring R. And this one is by definition, it is the ith homology of this chain complex. Not of this chain complex, but okay, I recall the resolution is this one. Okay, so without resolution is the sequence which has homology M here, and so you also need to consider this complex. So just of complex, this resolution P must be tensored over a group ring with N, and this is a definition. Similarly, one instead of taking a tensor with N, one can take home to N. Then you home again over the G. And then you have cochain complex. You have complex with differentials in this opposite direction. So x, ith over the G from M to N is again by definition the homology of this cochain. But now it is better to say that this is cohomology, the ith cohomology of this cochain complex. Okay, so this is just definition. And what I'm going to say, the most important claim here is that these functors, it is rather easy to see that it will be rather easy to see after I, proposition is that these objects are well defined in a sense that they are independent after the choice of project resolution. So, proposition is that Tor and X are independent of the choice of resolution. But it is important that resolution is projective. Of the choice. I will prove this for Tor, and for X it is completely similar. And so I will skip this proof for X.
So here n and m are z module, and the resolution is over.
No. All objects are G modules. All modules are modules over the G. But M and N are of course not assumed to be projective. If they itself are projective. Okay, this is a very good, point. That okay, if we look, suppose that N is projective, then the tensor product with N is an exact factor. So it takes an exact sequence. Well, this sequence is not exact. It will be exact if we add M here. But it takes to M here. So all Tors are, let us start with, let us start with one trivial thing. What is Tor 0? I claim that this one is just the tensor product of M over G. The matter is that we know that this was an exercise. We know that the tensor product with N is right exact. So in this rightmost case, here we will still have this sequence was exact. So right exactness means that if I take here, I can always delete here and if this was T1, yes, then I can always do as follows. I can write here T1 over kernel of T1. Then this will be a short exact sequence. Okay. This is no longer projective, but I will always have this short exact sequence. Applying tensor product with M, I get that this is not important for me at all, but here this one is exact sequence. So it is exactly this term. So if I write without this, then the homology is exactly this. So it follows from right exactness that
What just happened?
Maybe I just would like to say that right exactness, which was an exercise, means that if I have such sequence, then after tensor by n, it will be exact in the last two terms, here and here. It will not be exact further, but in these two terms, here and here, it will be exact. This is exactly right exactness. But this means that I need exactness in this term. This means that, what is exactness? That the image here coincides with kernel here. So if I delete this one and just send it to 0, then it is not exact, but the homology is exactly this module, the tensor product. if it was exact with this formula, then how do you want? So here the homology is exactly this. Similarly, the last x, since home is left exact, we similarly have that this one is just home over g from m to n. So the zeroth functions are not interesting. They are the same as initial functions. We started from tensor product and from home, and zeroth tort and zeroth x are exactly them. But higher tort and x are new functors. And well, and what I want to say, assume that n itself is projective. Well, if n itself is projective, then the tensor product with n is an exact function. We have already discussed this. That projective modules are flat, so the tensor product with it is an exact function. Then this sequence will be exact except for, well, it will be exact if I consider this one. Then all higher torts are trivial. So if n is projective, we see that if n is projective, then these torts are trivial for positive I. Similarly for x. But look, if n is projective, then we can argue in another way. If m is projective, then it has a very simple projective resolution. This one. So if I transfer this projective resolution by n, and of course it will have homology only that in grade 0, since it's just is 0 everywhere. So if m is projective, then the same. So if at least one of the modules is projective, then the torque is also trivial. Okay. It's time to stop. Yes. Well, now I just would like to say one thing, that there is another good exercise which is not so easy, and maybe we can discuss it sometimes if we have time. That the function home is not symmetric, by the way. It's covariant in one variable, contravariant in another. Of course, it's not. But the tensor product is symmetric. When our ring is a group ring, and we can consider it as a function of category of left G modules, then it becomes symmetric. The tensor product of m and n is naturally isomorphic to the tensor product in another direction. However, the definition of torque, well, m and n play different roles in the definition. Nevertheless, there is a natural isomorphism of torque m and torque m. This is what we discussed at some point, but not today. But, well, as for today, now we have maybe a 15 minutes break, I think, till 6. And after that, I will prove this proposition, and after that we will together consider some examples. Okay. Надо выключать или не надо?
Можно не включать.
Я не умею.
Я тоже не умею.
Тише. Это пример.
Всегда что-то так сказали, что нулями это самое важное, что вообще есть. То есть мы как-то...
Нет, да, я просто что-то я забыл про это.
Нет, мы что-то как в какой-то момент думали, почему так важно, чтобы, ну, когда вы берете там производную функцию, почему важно, чтобы изначально функция была с какой-то стороны точек, а с другой стороны берете производную, зачем это условие точности. Вот, и вроде ни в каком месте не нужно, кроме вот, непонятно, именно этого условия, ну, а это условие придает смысл как бы всему происходящему.
Ведь вообще никакого не нужно.
Ну, что-то кажется, что на самом деле...
Нет, ну определить-то можно.
Ну, определить можно, определить там заменку.
Нет, понятно, да. Прям не нужно, да?
Сейчас, может быть, я вру, потому что начнет от резолента зависеть.
Может быть, да, вот мне сейчас тоже...
Сейчас. Это что-то не подумал.
It's
No, I just can't see the.
Yeah, yeah.
I just
Well,
can't
yeah,
see where it's hard. I mean, but I don't have any word to think about.
I
Well,
don't.
actually, there is a book, but it's a collection of books there.
Well, but okay, also have no ideas how to think of it. Well, so when you asked me, I tried to think whether I see some arguments in favor of positive or negative answer. And I understand that I don't know.